A newborn closes its hand around your finger and grips hard enough to hold its own weight. No one teaches an infant to do this. We recognize it as a beautiful, intimate moment, but the instruction driving it arrives completely unlearned. That grip is a 60-million-year-old survival mechanism. It was engineered for a primate infant clinging to its mother's fur while she moved swiftly through the trees. Losing that grip meant falling, so the reflex had to be strong, immediate, and completely automatic. The infant is gone, the trees are gone, and the fur is gone. Yet the reflex remains, wired into a human nervous system that has never been told to stop. Evolution left this program running quietly inside you. This diagram shows exactly how a baby's nervous system processes that action. The palmar grasp, along with the Moro reflex, where a baby throws its arms outward when it feels a sudden drop, operates on a simple spinal arc. The signal travels from the hand directly to the spine and bounces back as a muscle contraction, bypassing the brain entirely. And if we look across the rest of the body, we find an entire network of similar legacy hardware. You have erector pili muscles attached to your hair follicles that reflexively try to puff up a coat of fur you no longer possess. You have Darwin's tubercle, a small point of cartilage on the outer ear left over from a more pointed mammalian ear shape. You even have a coccyx at the base of your spine, the fused bone remnant of an ancestral tail. Then there is the palmaris longus, a slender muscle in the forearm used for grip strength in tree-dwelling primates. Between 10 and 25% of humans today are born without it. If you lack this muscle, you will experience absolutely no functional deficit to your grip or arm strength. Because of that uselessness, reconstructive surgeons highly prize the palmaris longus. When they need a donor tendon graft to repair a torn ligament elsewhere in a patient's body, they harvest it from the forearm. Your body is running redundant hardware that only becomes useful when modern medicine needs spare parts. Beyond visible structures, the molecular layer of our biology contains even more definitive fossils. This diagram shows a sequence of DNA responsible for synthesizing vitamin C internally, an enzyme process most mammals use to stay healthy. Humans cannot do this because the specific gene responsible, gulo, was broken in a shared ancestor roughly 60 million years ago, leaving behind a silent pseudogene we now call gulo-P. Notice what happens when we map this sequence outward. Because that single ancestor presumably ate a diet so rich in vitamin C that losing the ability to manufacture it carried no survival cost, the mutation was carried forward. The exact identical genetic damage is found in every descending ape and monkey tested today, serving as a permanent historical record. Unlike almost every other mammal, a human deprived of dietary vitamin C will develop bleeding gums, failing joints, and eventually die of scurvy. That disease exists today exclusively because a biological backup system was permanently switched off tens of millions of years before the first human existed. When 19th century comparative anatomists first started cataloging these rudimentary human structures, they struggled to interpret them. In the 1870s, Charles Darwin cautiously listed a few examples, pointing out the newborn's grip as an inherited mechanism. To this day, the grasp reflex is still occasionally referred to as the Darwinian reflex. In 1893, the German anatomist Robert Wiedersheim formalized Darwin's observations into a sweeping catalog. Operating purely on the structural anatomy visible to him at the time, Wiedersheim published a list of 86 human organs he classified as completely functionless vestiges. By the 1920s, commentators had expanded that list to 180 useless human structures. At the 1925 Scopes trial in Tennessee, this expanded catalog was read directly into the court record, presented as unquestionable evidence that the human body was a walking museum of antiquities. As 20th century medical science advanced, researchers steadily crossed organs off Wiedersheim's list. The thymus, he thought useless, was actually training the immune system's T cells. The pituitary gland was the master regulator of the body's entire hormonal system. Anatomists were confident these organs were obsolete, when in reality, their tools simply weren't advanced enough to measure immune signaling and hormones. What we understand now is that evolution rarely deletes, it suppresses. This diagram illustrates how a healthy adult brain manages its ancient codes. As the frontal cortex matures in early childhood, it actively builds inhibitory pathways down the spine. These physical blocks hold primitive reflexes in check. But when frontal lobes sustain damage from a stroke, a tumor, or Alzheimer's disease, the suppression network collapses. The inhibition fails. Without the higher brain locking them down, those exact ancient newborn reflexes reappear. Neurologists call these frontal release signs. Recent longitudinal research following cognitively intact older adults found that those exhibiting 2 or more of these returning primitive reflexes were nearly twice as likely to go on to develop dementia. These 100-million-year-old circuits are now functioning as an early warning system for cognitive decline. Testing for a grasp reflex decades after infancy signals a drastically different medical outcome. The biological program is identical. The survival context is reversed. Somewhere tonight, a neurologist will stroke a patient's palm and watch for that exact same grip. What does it tell you when the past switches back on?